Angled-Wall-Induced Capillary action for different biofluids in microfluidic sensing.
Is it audible?
Okay, so outside of the presentation, first I will go through the how microchannel is used for biomedical devices. The of microchannel is constant circulations, the which vessels are used for circulation.
Audible? Okay. Because
Microchannel is a very fundamental part of any microfluidic system. In general, for biomedical devices or biosensor, uh, microchannel is generally used for biofluid collection, also via micro needles. Further drug delivery also can be done by that. And blood separation microreactors, we need to study how biofluids interact with each other, different biofluids interact with each other in a microchannel. And to mimic and study the fluid mechanism of biofluids and other chemicals in a microchannel, we need to have a lab on the chip. For that also we need microchannels. And other applications like fuel cells and disease diagnosis, drug discovery and delivery, disease modeling, tissue engineering, organ energy, point of care testing. These all can benefit of design of various microchannels and how different fluids interact inside a microchannel. To see the effect of different geometrical structures on capillary action of different biofluids inside microchannel. We have considered two kinds of geometry here. One is conventional cylindrical one. Here is the reservoir from where the biofluid will come and get out through the outlet. And similarly, another is angled wall. So with respect to the reservoir, the wall of the microchannel is having some angle. It is designed such a way that the average thickness around the average thickness all the way through the microchannel is remain constant, that is 200 micrometer, which is equal to the cylindrical one. Further, the angled wall has three different values. One is 5 degree, 10 degree, and 15 degree, and all the microchannels has a height of 800 micrometers. And finally, we will compare how the velocity and pressure uh, have developed inside the microchannel during the capillary action. The mass and momentum transport for the fluids uh, having constant density is modeled by Navier-Stokes equation as given here. Further, there are three kinds of biofluids that have been taken. One is interstitial fluid, the second one is blood, another is saliva. These biofluids are very much essential for different biomarker detection and disease diagnosis. Further, to study how these biofluids will behave inside a microchannel, we can design further biomedical devices for biofluid collection and biosensing. Here, these three biofluids have similar kind of density, but varying viscosity. So with that, with this and the governing equation, we will see how these affects and with the geometrical structures, how the fluid flow changes inside the microchannels. Here the figure shows two kind of structure. One is cylindrical one. The other one is the angular structure, that is with theta is equal to 15 degree. And we can see here the built-up pressure inside the microchannel. For angled wall structure with theta is equal to 15 degree, the built-up pressure is 14.85 kilopascal. You can see here the maximum one is at the top, which is more than that of cylindrical one, which is 2.56 kilopascal. We can attribute this with the uh, component of surface tension force along the direction of flow. So as the angle of the wall is increasing, there is a component, the value of component of the surface tension force along the direction of flow will increase, which generally with greater force, the greater pressure will come, and the fluid will go with more force, and the pressure will be increased further, and it will go with uh, bigger height. Here it is going up to 530 micrometer. When for cylindrical one, it is going up 405 micrometer. This graph shows the rise in fluid color against time for interstitial fluid. Uh, the first one, the black color one, is the first cylindrical one, and other one as theta goes from 5 degree 15 degree for angled wall structure. We can see from the graph that in the beginning, the radius of this cylindrical wall structure has a radius of around 200 micrometer, but the angled wall structure, it has the radius is R1, that is 200 micrometer plus the amount 400 tan theta micrometer. So due to this one, the radius R1 is larger than the cylindrical one. So for that, the in the beginning, the cylindrical one, the flow, the rise in column is much more than the angled one, because the height with respect to time, the derivative is the slope, that is the speed. The speed increases first, but as the fluid moves upward, the radius increases and goes up to R. So the rise in the fluid column increases towards the higher angle value, that is theta is equal to 15 degree for this one. So the structure with a higher theta value takes overall less time to fill itself completely, as opposed to the cylindrical one. Here this graph shows the rise in fluid column for interstitial fluid, then the blood for saliva in all the four structures, cylindrical, all the angle or inclined wall structures. So to fill the structure 2 with theta is equal to 15 degree angle wall structure, completely it requires 0.88 millisecond for ISF, 0.925 millisecond for blood, and 0.975 millisecond for saliva. Similarly, for cylindrical channel, it requires 1.35 millisecond for ISF and 1.425 millisecond for blood, and then for saliva, it is 1.55 millisecond. So overall calculation shows that our angle wall structure gives a fast response than the cylindrical one, around 34.8%, 35.088%, 57.909% for ISF, blood, and saliva respectively. Here we can see with different kind of biofluid, like for ISF, blood, and saliva, the densities are around the same as we discussed previously from the table, but the viscosity increases from with ISF, blood, saliva. So due to this increase in viscosity, when we put it in Navier-Stokes equation, the lossy part will increase, so the capillary rise will decrease with the increase in viscosity. Further, the capillary action is also dependent on the material used for the microchannel boundary wall or microchannel material, because the lyophilic property of the material will determine the wettability of the channel material that will form the contact angle between the fluid and the boundary wall, which will affect the rise in capillary or the capillary action. So here we can see the surface tension force responsible for the capillary rise is related to contact angle sinusoidal. And here contact angle is taken as theta Ca, and it is non-linearly related cosine of the theta minus theta Ca. And the graph here shown how with increasing in contact angle, the time required to fill the microchannel increases. So here to simulate different material, here we change the vary the contact angle from 0 to 80 degree, and we see what is the trend in required time to fill in. So here you can see as the contact angle increases towards the 80 degree, the flow the rise of the column will be slower and slower, and it is non-linearly increasing. And from the plot, you can deduce that when comparing to the cylindrical wall structure, the angled wall or the inclined wall structure with theta equal to 5 degree, 10 degree, and 15 degree takes less time to fill itself with for ISF 40.63%, 56.62%, 65.75% less time than the cylindrical counterpart. So hence the angle wall structure or the inclined wall structure becomes more effective also with an increase in contact angle, that is theta CA. So in conclusion, we have seen that use of inclined wall microchannel provides faster response when compared to the cylindrical one, and further it also more effective when the contact angle is higher. But there is a drawback when the inclination angle theta increases for a constant volume. So what happens is during the rise of biofluid column, in the initial stages, the radius of its base will be much more. So it will hinder the starting of the capillary. So the design of the microchannel should consider this also while designing with a better response. Next is with proper selection of the material, we can have a better contact angle, lower contact angle, so that it can be used in microneedles or microchannels for different microfluidic sensors in healthcare sectors. Further study in this direction would include the different techniques like capillary mixing, capillary electrophoresis in microfluidics domain to see how the different biofluid act in the microchannel when we will apply it when it is under different applications. Thank you.